Okay. So we were looking into the um, size reduction, if I remember correctly, from mechanical operations, and we looked at some of the basic concepts with regards to size reduction, then size reduction equipments, various types of crushers, rollers, ball mills, and yeah, and we just started a brief introduction towards sieving or screening. So we'll start with that. Let's yeah. So we were just starting the concepts of screening. So screening, as I mentioned, you must have seen it, in your households, or even one of the best examples that I can remember is the screening of sand at construction places. So they'll have a screen, with very very small openings, and they'll pour sand on top of this, and this is to like make sure all the sands are like properly sieved, and the coarse particles or stones or the clumps are separated from the sand for construction. So that is a very common example that I can think of. Then you must have done this for a lot of powders, the masala powders and all that at home. So all these things are basically some of the common applications that we see from day to day with regards to screening. So yeah. So when we talked about screening, we talked about the different sieves and how these sieves are represented using mesh numbers. And we defined mesh number, which is basically the number of openings per square inch. So yeah. So now let us look into a term called effectiveness of a screen. So let us just draw a brief block diagram of the screening process. Let us say we have a feed F, okay, and let's say we are passing it through a screen, and let us say we get the top product as D and the bottom product as B. So this top product is called as overflow, or the one that is not passing through the screen. So let's say if the screen size is 1 mm, this overflow, the size of the particles in the overflow will be greater than 1 mm. And so conversely, this B is called as underflow. And in the underflow, the size of the particles will usually be less than 1 mm. So this is the feed F, and we have the overflow and the underflow D and B respectively. Let us say XF is the mass fraction of feed, XD is the mass fraction of the overflow, and XB be the mass fraction of the underflow. So this XF, XD and XB, these are the mass fractions defined with respect to the overflow products. Now, how this is defined, we'll look into it in a while. But just keep in mind these mass fractions are defined based on the overflow products. So for this, we can start writing all these basic mass balances. Feed is equal to the overflow plus underflow, and the component balance F into XF is equal to D into XD plus B into XB. So you can write these two mass balance equations, and from these mass balance equations we can find the effectiveness of a screen. So as I said, these mass fractions XF, XD and XB, and these are mass fractions defined based on the overflow products. That means, let's say we are fixing a size of some, just we'll take some arbitrary value, like let's say some 0.1 mm. Okay, so when you say XF, so XF means the fraction of the feed particles which has a size less than or equal to 0.1 mm. Okay, so that is how you define these mass fractions. So then XD will be the fraction of particles in the overflow that has a size less than 0.1 mm. So this 0.1 is just an example arbitrary value. It can be anything. It depends on the system or the situation that we are dealing with. But just letting you giving an idea of how these mass fractions are like generally defined. So that is how these mass fractions are defined. And using this, we can write the mass balance and the component balance equation 1 and 2 respectively. And using this, you know, we can combine. Let's write this equation again. We'll write F is equal to D plus B and Fxf is equal to dxd plus B into xb. Now from this, we can rewrite this top first equation as D is equal to F minus B, or we can even write B is equal to F minus D. So substituting the values for B or D in your second equation, we can get something like, let us substitute the value for B for here example. So Fxf is equal to dxd plus F minus D into xb, and we can rewrite this as D by F is equal to xf minus xb by xd minus xb. This is just a simple rearrangement of this equation here. So let us take this as equation number 3. And similarly, if we substitute this D is equal to F minus B in this equation, we can get something like Fxf is equal to F minus B into xd plus xb into b. And if we rewrite this, we can write B by F is equal to xf minus xd by xb minus xd. So let us say this is equation number 4. Now the effectiveness of a screen is usually represented as epsilon. This will be equal to D into xd by F into xf into B into 1 minus xb by F into 1 minus xf. And you can say the first term is called as recovery and the second term is called as rejection. So this is the general equation for the effectiveness of a screen. Now we can elaborate this equation using the mass balance, equation 3 and 4. But this is the basic, equation for your effectiveness of a screen. So if we apply the mass balance equations 3 and 4, we can get epsilon is equal to xf minus xb to xd minus xf to 1 minus xb into xd by xd minus xb the whole square 1 minus xf into xf. Now here we did nothing but just substituting for d by f and b by f in this equation using these two equations 3 and equation 4. And when we substitute that, we get this elaborate equation for the effectiveness of a screen. Right. Now when I say these mass fractions xf, xb, xd, so as I said, these are usually defined based on overflow products. You can also define it based on your underflow product. So if you are defining this in terms of your underflow product, you will have to write these mass fractions as xf dash, xb dash and xd dash. And let's say xf dash will be basically 1 minus xf. So when we say xf dash, which means, which means these are based on the underflow products. So let us say you have we'll just take the last arbitrary value that we took 0.1 mm. So let us say we need particles to be separated based on whether they are greater than 0.1 mm or less than 0.1 mm. So xf means number of particles that are less than or equal to 0.1 mm in feed. But then xf dash, which is based on the okay, there is a slight confusion here. So this is actually greater than equal to, because it's overflow, right? Yeah. So xf dash will be particles having size less than 0.1 mm in the feed. Just 1 second. Yeah. Yeah. So yeah, we were defining these mass fractions, right? Yeah. So as I said, XF, when you are trying to define it based on the overflow means the particles that are greater than that size. So last page I said it's less than this size. It's actually greater than 0.1 mm. So this will be overflow, and that is how if you are defining it based on overflow, it will be greater than 0.1 mm, and if you are defining it based on the underflow, it will be less than or equal to 0.1 mm. and this relationship is also there. So xf is 0.1, means xf dash will be 1 minus 0.1, and that will be 0.9. So just to make a note of it. But yeah, you can define this based on xf dash as well, and you can have the same equation for effectiveness. Just replace this xf with xf dash, xb with xd dash, and xd with xd dash. So again, the effectiveness in with respect to the underflow will be xf dash minus xb dash into xd dash minus xf dash into 1 minus xb dash into xd dash by xd dash minus xb dash the whole square into 1 minus xf dash into xf dash. Right. So this is the equation for effectiveness of a screen. Right. So just one more thing, one more concept that I wanted to let elucidate today. So it is the centrifugal separation. So centrifugal separator, it's basically something like a sedimentation basically, but you know applying the centrifugal force. So you must have heard something, some of the equipments like cyclone separator. So these things are basically separators which separate your particles based on the by using the centrifugal force. And there are even things like centrifuge to separate two liquids of different densities and so on. But anyways, today we'll be looking into specifically into cyclone separator. So cyclone separator, just drawing a very simple uh, diagram. So you will have a particle, let's say this is the particle. This particle will enter this chamber, cyclone chamber, tangentially to the walls of the chamber. And what happens is this induces a centrifugal force as well as gravitational force. And this particle from here, it will start rotating and rotating, and finally it will get separated to the bottom. So this is basically the mechanism of a cyclone separator, and we define this particle here. So just drawing this a bit bigger. So we have this particle here. Now there are two forces that acts on this particle. So one is the gravitational force, which is basically mg, and the other is the centrifugal force, fc, which is basically mr omega square. Right, and this mr omega square, you can write it as mr into v by r the whole square, because angular velocity omega, you can write it as v by r, and this will become m v square by r. So this is the centrifugal force. Right, now these two forces acts on your particles in a cyclone separator, and at equilibrium, this centrifugal force will be equal to the gravitational force, or that means mg will be equal to mv square by r, or mr omega square. This is the force balance principle that we use to derive the equation for critical speed of a ball mill, if you remember correctly. So there also we will be taking the equilibrium between the gravitational force with the centrifugal force. So here also pretty much the same. When the particle is at equilibrium, the gravitational force will be equal to the centrifugal force. But this is not required in a cyclone separator, because if this is at equilibrium, that means this particle won't be moving downwards. It will just keep rotating like this, because both these forces are in equilibrium. So we don't need this equilibrium here for a cyclone separator. What we do need is something called as a separation factor. And the separation factor is basically the ratio of the centrifugal force by the gravitational force. So the centrifugal force was mv square by r, and the gravitational force was mg. So you can cancel this m and m, and it will be v square by rg. So this is called as the separation factor of a cyclone separator. And one more thing we need to learn regarding to this cyclone separator is the collection efficiency. Say it is eta, and this eta will be basically equal to weight of the collected solids by weight of the feed. So this is called as the collection efficiency of a cyclone separator. So we'll see how we can use these equations for solving some set of problems in the coming slides. So what we'll do is we'll stop here with the theory and all that. We'll try to solve some questions today with regards to this and see where it goes. So yeah, I hope these things are pretty much okay-ish or clear to you. Um, you can always ask if there is any doubt, and if everything is fine, we can move on to the questions. Fine, then we'll move to a question. Okay. Just a moment. It's question number 11. Okay. Okay, right. Fine. Let us start with the questions. Okay. There is a question from GATE 2016 from Chemical Engineering. Question number 7. In a cyclone separator used for separation of solid particles from a dust-laden gas, the separation factor is defined as the ratio of the centrifugal force to the gravitational force acting on the particle. SR denotes the separation factor at a location near the wall, that is at radial distance r from the center of the cyclone. Which of the following statements is incorrect? Option A, SR depends on the mass of the particle. Option B, SR depends on the acceleration due to gravity. Option C, SR depends on the tangential velocity of the particle. And option D, SR depends on the radial location R of the particle. So this is a question from cyclone separator from mechanical operations, and the reference NPTEL lecture can be found in Unit 3, Lecture 15, Size Reduction Equipment to Mechanical Operations by Professor Shavina Khanam, Department of Chemical Engineering, IIT Roorkee. So here in this question, they have given a cyclone separator of radius r, and a particle is undergoing two forces, a centrifugal force Fc and a gravitational force Fg. And by definition, the separation factor Sr is given as the ratio of the centrifugal force to that of gravitational force, and that means Sr will be Fc by Fg. Now the centrifugal force can be defined as mr into omega square, and the gravitational force can be represented as m into g. Now this can even be simplified by taking omega, which is the angular velocity, is equal to v by r, where v is the tangential velocity. So this mr omega square will become mr into v square by r square, the whole by mg. Now in this equation, we can cancel out a lot of terms. So the m will get cancelled in the numerator and the denominator, and this r will also get cancelled once here. So the final equation for the separation factor SR will be equal to V square by RG. Now here V square is the tangential velocity of the particle. So that means SR will depend on the tangential velocity of the particle, which means option C is true. It is not incorrect. It is correct perhaps. And V square by Rg, so it also depends on R, which is the radial location of the particle. So option D is also true. And G is the gravity, so option B is also true. The only thing that is not true out of these four options is option A, because the mass term gets cancelled in the numerator and denominator for the separation factor. So separation factor is independent of the mass of the particle. So that means out of these four options, the incorrect statement is option A. Separation factor SR depends on the mass of the particle. So option A is the right answer here. Right. So just this is basically just a repetition of what we just did in the last few slides. So the separation factor will basically depend on v square, or the velocity, tangential velocity of the particle, radial location of the particle, as well as the gravitational force or acceleration due to gravity. It is independent of the mass because the mass term gets cancelled in the numerator and the denominator. Right. So let's move on to the next question. Okay. So this is a question from GATE 2011 from Chemical Engineering, question number 35. The particle size distributions of the feed and the collected solids sampled for the same duration for a gas cyclone are given below. What is the collection efficiency in percentage of the gas cyclone? And the four options given are option A 31, option B 60, option C 65, and option D 69. So this is a question from cyclone separator part in mechanical operations, and the NPTEL lectures can be found in Unit 2, Lecture 7, Effectiveness of Screen Mechanical Operations by Professor Shavina Khanam, Department of Chemical Engineering, IIT Roorkee. So here they have given us 6 different ranges of particles. 1 is to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and 25 to 30. And they have given us the feed of the particles in these size ranges as 2, 3, 5, 6, 3, and 1 respectively. They have also given the weight of the collected solids in this size range as 0.1, 0.7, 3.6, 5.5, 2.9, and 1. And using this table of data, we need to find the collection efficiency or overall collection efficiency of the gas cyclone in percentage. So we have defined that the collection efficiency of a gas cyclone, which is represented as eta, is equal to weight of the solids collected by weight of the feed. And if we need it in percentage, this will be into 100. Now what we have to do is we have to apply this collection efficiency formula for each of these different size ranges separately. So let us take the size range as range 1. This let it be a range 2, 3, 4, 5, and 6. The collection efficiency in size range 1 will be eta 1, and that is equal to weight of the solids collected in this range. So weight of the solids collected in this range is 2 . sorry, the weight of the collected solids in this size range is actually 0.1, and the weight of the feed will be 2. So the collection efficiency in the size range 1 will be eta 1, which is weight of the collected particles 0.1 by weight of the feed, which is 2. And this will be equal to 0.05. Now similarly, we can write efficiency in the size range 2 as 0.7 divided by 0.3. So that will be 0.7 divided by 3, and this will be equal to approximately 0.233. The efficiency in the size range 3 will be equal to 3.6 divided by 5. So 3.6 divided by 5, and that will be equal to 0.72. Efficiency in the range 4 will be 5.5 divided by 6. 5.5 divided by 6, and that will be equal to 0.917. Efficiency in the size range 5 will be 2.9 divided by 3. So 2.9 divided by 3, and that will be 0.967. And the efficiency in the size range 6 will be 1 by 1, and that will be equal to 1. So these are the individual efficiencies in the different size ranges given in this question. Size ranges 1, 2, 3, 4, 5 and 6. Now here we need to find the overall collection efficiency. So we can define the overall collection efficiency as eta overall is equal to eta 1 x1 plus eta 2 x2 plus etc. up to eta 6 x6, where x is the mass fraction in that size range. So here in this equation, we have found the values for eta 1, eta 2 up to eta 6. Now we need to find the mass fraction of these particles from the size range 1 to 6. And the mass fraction x will be equal to weight of the particles in that size range by total weight of the feed. Now for example, in the size range 1, x1 will be weight of the particle in that size range, and that weight of that feed in the size range will be 2. So this will be 2 divided by total weight of this feed, and the total weight of the feed can be obtained as the sum of all these feeds in the different size ranges. So this will be equal to 2 plus 3 plus 5 plus 6 plus 3 plus 1, which will be 20 gram. So the mass fraction in the size range x1 will be 2 divided by 20, and this will be equal to 0.1. Similarly, we can find the mass fractions of these particles in the different size ranges. So x2 will be 3 by 20. that will be 0.15. X3 will be 5 divided by 20, and that will be 0.25. X4 will be 6 divided by 20, and that will be 0.3. X5 will be 3 divided by 20, and that will be 0.15. And X6 will be 1 divided by 20, and that is 0.05. Now we can also check this by taking the sum of all these mass fractions and seeing if this sum of mass fractions becomes 1. So here 0.1 plus 0.15 plus 0.25 plus 0.3 plus 0.15 plus 0.05 will be equal to 1. So the mass fractions that we have obtained here is right. Now all we have to do is substitute the etas and the mass fractions x in the overall equation for collection efficiency. So eta overall will be eta 1 x1 plus eta 2 x2 plus etc. up to eta 6 x6. So substituting this, we'll get 0.1 into 0.05 plus 0.15 into 0.233 plus 0.25 into 0.72 plus 0.3 into 0.917 plus 0.15 into 0.967 plus 0.05 into 1. And if we do this whole sum, we can get the eta overall as 0.69. And since we needed this overall efficiency eta overall in percentage, we can just multiply this by 100 and we can get the overall efficiency eta overall as 69%. So the right option here is option D, 69%. Right? So yeah, basically what we did is we had the efficiencies and the mass fractions. We could find it using these tables at different size ranges, and in order to find the overall efficiency, we just had to apply this overall formula. Eta overall is equal to eta 1 x1 into eta 2 x1 in eta 1 x1 into x1 plus eta 2 into x2 plus eta 3 into x3 etc. up to eta 6 into x6, and just substitute all these values here and you can get the final overall efficiency as 69%. Fine, let's try to solve one more question for today. So this is a question from GATE 2007 Chemical Engineering, question number 11. In Taylor series, the ratio of the aperture size of a screen to that of the next smaller screen is, and the options are 1 by root 2, root 2, 1.5 and 2. So this is a question from screening part in mechanical operations, and the reference NPTEL series can be found in Unit 1, Lecture 4, Characterization of Collection of Particles 1, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here, let us take two meshes in the Taylor series, and these are adjacent sizes. So let's say this is size 1 and this is size 2. These are the adjacent sizes in a Taylor mesh series, and they want us to find what is the ratio of the aperture size of this screen to that of this screen, right? So let us just take these two screens. Okay, now assume, this is the mesh number. Let us say this is mesh number 1, just taking an arbitrary value. So there is only one mesh per square inch, and let us take the smaller one as mesh number 2. So that means in that same 1 square inch we'll have two meshes. Now let us say this has an area A1, which is the larger mesh here of mesh number 1, and the bottom one, let us say each of these openings have an area A2, right? Now by Taylor series says that A1 is basically equal to 2 into A2, right? So now let us say L1 is the length of this screen of having area 1 A1, and let us say L2 is the length of this opening having an area A2. So then area A1 will be L1 square and area A2 will be L2 square. So again, by Taylor series, we said that A1 is equal to 2A2. So that means L1 square is equal to 2 into L2 square, or L1 square by L2 square is equal to 2, or L1 by L2 is equal to root 2. So this L1 by L2 is the ratio of the aperture size. So L1 by L2 will be root 2 for the Taylor series. So here option B, root 2, is the right answer. Right? Okay. So let us stop here for now. We still have a few more portions to cover in mechanical operations, and hopefully in the next 3 classes we'll be able to finish these portions. So mostly what is remaining is solid liquid separation. So you have settling of particles, free settling, hindered settling, and so on. And then you have, centrifugal sedimentation, or basically centrifuge, and the, separation equations for centrifuge and so on. And then there is one good topic called fluidization, you know so it includes, pressure in a packed bed, eigen equations, and so on. And yeah, let us see how far we can go with this in the next three classes. But yeah, let us stop here for today. If there are any doubts, you can always, unmute and speak, or type in the chat box or whatever. Or you can even, if you are not able to solve some questions also, you can always, email me those questions, and we'll try to solve them in the class. And yeah, that's it for today. And thank you for joining. And if there are no doubts, that's it for today. And yeah, I'll see you all next Monday.